We're very excited to have Edith Cohen from Tel Aviv University and Google Research to tell us about sampling the ideas in Sublinear algorithms.
Yeah, thank you, Clement. Okay, so most of what I'll talk about is classic stuff, but it's a very useful toolkit that I think people should know about. So just random sampling is basically basic of learning from observations, and it has a long history for centuries. Sampling had been used to estimate population size, and then there was the development of statistics. In recent decades, it was also a ubiquitous tool in efficient processing of data sets and large data sets, part of analysis and algorithms design, as we had seen in the last talk. So I will cover some very selected ideas that are influenced by what I'd used or developed over the years. Sample is viewed as a summary structure. There is a data set of key value pairs. Here X is the key, WX is the value. And a sampling scheme is basically specifies some randomized summary structure of the data set. And the sample has the form of a subset of the keys, but also we will sometimes need to keep some auxiliary information. So basically the idea is you have the big data, you sample it, and then you want to estimate all sorts of things on the data. So instead, you apply an estimator to the sample, and or sometimes you have samples of kind of multiple data sets, and you want to kind of estimate a function of these multiple structures from their samples. So the variations here are specifying the sampling schemes, these mappings, and the estimators, which are essentially the query response algorithm, what we apply to the samples to estimate what we want. And there are we look at trade-offs of accuracy versus sample size, but also we look at efficient algorithms in terms of storage, communication, compute. And this is because there is a very big differences in the raw data presentation. It could be distributed, it could be streaming, it could be unaggregated, it could be in the form of a graph. To compute the sample, we need to be mindful of that. So here is the other component. There is raw data in some form, and from that, over that, we specify the data set, and then we apply the sampling scheme. So one idea that is kind of very useful and important, and you must have seen it before, is to design composable data structures. So if we have a summary or a sample of data A and another one of data B, we should be able to construct a summary of the union of the data sets from the two summaries of the data sets. And this is a very useful property. So why do we want to do it? Because it's very useful with distributed and parallelized computation. Because if these are different parts of the data, we can summarize each one locally, and then we can combine the summaries. So basically, it helps us a lot on communication. It also allows us to parallelize the process. It's also very useful in streaming when data elements arrive one by one. And then we keep a summary, and then we see another element, so we don't need to go back to the original data. We just kind of can compute a summary of the old data plus the new item. And sometimes we can design things that work in a streaming model but are not generally composable, and that can be very limiting. Like in practice, usually we want things to be fully composable, but a fully composable, of course, does the streaming context as well. Okay, so now, okay, so one of the simplest and most useful things we want to do with the sample is kind of estimate linear queries. So we have our data set and we have a sample, and the query is specified by, say, some predicate that says which elements in the universe are in and which are out. And then we want to estimate the sum over the keys in the data set that satisfy the predicate of the weights of these keys. So this is one of the most basic things we want to do with samples. And usually we can do it with the following type of error bounds. So this Q just depends on how much of the data weight-wise satisfies our predicate. And then we can get an error that is essentially behaves like 1 over square root of the sample size, and we pay for this Q, this ratio. So this is, but to get these bounds, we need to use a sampling that is proportional to size, a probability proportional to size type of sampling. It's also called weighted or important sampling. Okay, so how do we get a probability proportional to size sampling schemes? So one basic scheme is to sample with replacement, which is basically we select each key proportionally to its weight divided by the weight of the whole data set, and we repeat this k times, so there could be repetitions. Then there is also sampling without replacement, and it's equivalent to the following process. We repeat k times. The first step is the same as the with replacement sampling. We select a key with probability that is proportional to its weight, and then we remove it from the data set, and then we keep going. And then there is another method, okay? So, and all these methods kind of yield the same worst case error bounds that we have seen. And there are different scenarios where we want to use each, but without replacement sampling is very helpful in practice because often we have data sets that are kind of heavy-tailed. That means that a lot of the weight is concentrated on few items, and when we do with replacement sampling, the number of distinct items that we get is much smaller than the sample size. And this also translates to us being able to do less accurate things with the answer queries less accurately over the data. So here we can see that the number of samples increases, but the number of distinct samples when we sample with replacement doesn't increase as much. So, okay. So now this is a very useful idea, sampling via order statistics. If you haven't seen it before, it's very nice. So basically, you can transform a sampling problem to a computation of an order statistics. And the gains here are often you gain efficiency. For example, sampling without replacement, as described, is a very sequential and inefficient process, and via that transform, you can do it very, very efficiently. And Also, sometimes it buys us being able to do more applications. We will see. For example, you can do the sampling without even knowing the total sum of the data set, the total weight of the data set. Okay, so it works like that. You just look at each key value pair in isolation, and you compute a score that is sampled from some distribution, that its parameter is the weight of the key. And usually, these are the two most useful distributions. Uniform between 0 and 1 over W, and this is known in the statistical literature as sequential Poisson, and then later was called the priority sampling, or using exponential distribution, and exponential distribution with parameter that is the weight. So these are the two useful ones. So to get sampling without replacement, you basically do this process, assign random scores to all the pairs, and then you take the minimum. And to get without replacement sample of size k, you just take the keys with k minimum scores. So this is like a almost classic result.
Sorry, so the model here is like streaming, or is like this data is just distributed somewhere and you're going to?
Yeah, so you can implement it in many different settings, but it's useful also for it's useful for distributed data, streaming, anything. Sometimes, I mean, right now it's just like I'm just discussing the way to do it, right?
So like for each object, you're going to assign a score to it.
Yeah, each object, yes, exactly. Thank you. So each key value pair, you assign a score, and that can be done locally. And then you aggregate to get the k smallest scores overall for a PPS4 sample, or the smallest each time. I mean, it's useful in, we'll see some examples of applications. So
I just have a silly question. I mean, like, why is it more efficient to aggregate the scores than the objects themselves? Because the objects you think are big and...
Because you want the end product to be a sample. And sometimes, so for example, if you want to do without replacement sampling, in some situations, you can, I mean, we will see situations where it's very, very useful, okay? Like for example, sometimes you need to know the total weight and you don't, or sometimes objects are repeated in some sense. Or, I mean, we will see applications. Okay, so why does it work? Okay, so what we did is we assigned a score that is the exponential random variable in the weight of the pair of the key value of the value. So basically, everything follows from basic properties of the exponential distribution. If you have two independent exponential random variables with different weights, then the probability that one is smaller than the other is proportional to their weight. That's a very useful property. The minimum of exponential number of variables, the distribution is the exponential random variable with parameter that is the sum. So it kind of gives you a minimum to sum to minimum transform, which is often very useful. And the memorylessness. The probability that the value is above some t0 plus t, given that it's larger than t, is basically that. So it's like, okay, so why does it work? So the first step is, so basically we sample by assigning exponential random variables to all the pairs and then taking the minimum one. So why is it equivalent to sampling according to the weight? The probability that x1 is smaller than the mean of the others is exactly the probability that item one, key one is selected. And we apply this property. So the minimum of the others is basically the sum of, is exponential random variable with the sum of the weights. and then we apply this property, and we get exactly the probability that sampling Q1 is just proportional to its weight. And why does it continue like that? Because then we use memorylessness. So after we take out one item, so basically if we subtract that value from all the others, we are in the same situation and we can repeat. Okay. So what does it buy us? So here is one application, raw data presented as a distributed streaming of pairs. We can locally compute the score for each pair, and then we just aggregate the smallest scores, and we get the result. So here is, so next we'll do another application that is kind of more nuanced, where this is helpful. This is graph sketches. So here the goal is you have a graph, and here the goal is to compute for each node of the graph a sample of the nodes it can reach, or a sample of all the nodes within certain distance from that node. And we want to do it for all the nodes in the graph. So for example, for these nodes, we want a sample of everything it can reach, which is this, which happens to be distance 1, but it doesn't have to. So the naive way to do it is to first compute for each node everything it can reach, and then sample that. And that's like a computation that is the number of nodes times the number of edges. But if we use the order transform, it's near linear. So we can compute a sample for every node in the graph from potentially all the nodes it can reach. So it could be n nodes in just a near linear time. It's basically sample size times the number of edges. And the idea is, so basically we compute a score for every node, and then we propagate the scores kind of backwards by increasing order. And that way, we will compute for every node the smallest k-scores that reach it. And the total computation is like, is just linear. It's every node is visited k times. So
these samples are all correlated, though. Like
yes, so the sample, yes, yes, exactly, and actually that's necessary. So it's nice because the samples are computed without knowing the cardinality of what the samples are from, and these samples can also be used to estimate the cardinality. And as you said, the samples are correlated, and we will get back to that because that's also a good thing. Okay. So now, okay, so this is these are two cases where this kind of techniques were useful. So now I'll talk a little bit on how you estimate linear queries from these samples. So one approach is that, and here you assume you don't just have the samples, you also have the scores, but you don't know the sum, but you want to estimate the sum. So this is a basic parameter estimation problem. Every score, okay, so without replacement sampling, every score is basically a sample from an exponential random variable with parameter that is the sum of the weights. And basically, we just want to estimate the parameter from a bunch of samples. And so there is an optimal kind of unbiased estimator, which is listed here. And this is a sufficient statistics, the sum of these weights, so it's kind of optimal. And without replacement samples, there are more exact ways to do it, but You can also use memorylessness to extract KIID samples equivalent with this distribution, and then we can apply the same thing. That's the simplest way to say. Okay. And there is another way that also allows us to estimate more general linear queries. So here we have our predicate, and we want to estimate the sum from the sample. So a very standard technique in statistics is to use inverse probability estimate. So basically, we look at what's in our sample and satisfies the predicate. And we add that weight divided by the probability of that thing being sampled. So this gives us an unbiased estimator for each one, because if it's in the sample, it's in with probability that it's the weight divided by its probability, it cancels out. So the expectation is the weight. So if it's not in the sample, it's 0. So the expectation is just its weight. So per key estimates are unbiased, linearity of expectation, the sum is unbiased. So this is a standard technique. But the way I described it, so this would give us kind of the optimal error bounds. But the way I described it, so it's very hard to do without replacement sample, because we cannot compute this probability very easily. And sometimes we need the total weight to compute these probabilities. But there is a way around it. And this is when you get like a sample with scores. And this is the general technique. You basically don't compute this probability exactly. You compute this probability conditioned on the scores of all other keys being what they are. So basically, for each key, you can look at the case lowest score of keys other than X, and then you can compute the probability that it's sampled conditioned on that, which is very easy to compute. You just every score is independent, so you just compute the probability that that score is smaller than what it would take to have it in, fixing the scores of all other keys. So you use that. And you get unbiased estimate this way. And it's, so we basically store the scores or store with the sample the case lowest score, and that's enough. But then, like, we did this conditioning, so how do the error bounds change? So the magic here is that essentially we still get this optimal error bounds. We lose almost nothing by it. So the argument, I don't know. So basically we can bound the variance for every key. We first bound it conditionally on what that threshold score is. And then we take the expectation over the distribution of the threshold scores, which we don't know, but we can find the distribution that statistically dominates it. And then the other component is to show that the covariance is 0 or less than 0. For different scores, so we basically get this optimal error bounds, the error bounds that we can get with probability proportional to size sample. We don't lose by this conditioning. Okay, another very useful idea is what we do when we sample according to some weights. But then our query uses kind of a different set of weights. So So this is useful in multiple scenarios. We will see some more later. For example, the weight changed, but we still want to use the same sample, or there are some limitations. So one thing to keep in mind is that when the new weights are sufficiently close to the old weights, we lose very little. We can still use the same inverse probability estimate, just the new weight that we want to use divided by probability that is computed according to the old weight. So it's still unbiased. And then basically when the weights don't deviate too much, ratio-wise, key-wise, we basically just need a little bit larger sample to get this same optimal for a smaller sample error bound with the new weights. So we don't get inherent error. We just get, we just need a slightly larger sample. So just keep it in mind. We'll see places where this is useful. Okay, another very useful idea is to use a sticky per key randomness. So here we want to attach the random bits of computing the score, not with the key value pair, but just with the key. So think about it this way. For each key, we can use a hash function sometimes, yeah, or there is an assignment of a seed value that is drawn from a distribution. But it doesn't depend on the weight. And then the score depends on the weight, but it's computed by taking the seed and dividing it by the weight. So this is just another way to get the scoring that we've seen before. So basically, exponential number random variables with parameter W is basically taking an exponential random variable with parameter 1 and dividing it by W. And the same with this priority sampling method. So basically, we just remember now, we just need to, we keep consistent seed value with keys. And what it buys us, so often there are situations where there is the same set of keys, but then there are multiple contexts that give it different weights. Let's call it like instances. And then if we use the same sticky randomness across all these samples, the samples are coordinated, and that has lots of benefits. Another useful scenario in this is unaggregated data. That the raw data is such that the weights are not explicit for each key. So the key appears in multiple places, multiple points of times in streaming, multiple servers. And then on each server, it has like a different weight. And basically, the weight that we want to use is some function of all these different weights. So in this case, again, the sticky randomness would really help us compute samples over the key value pairs that we want, where the values are not explicit. Okay, so this is just like some visualization. These are instances, so it's the same set of keys. It's data for Monday, all search queries from Monday, all search queries from Tuesday, I don't know what, yeah, whatever, and or network traffic or whatever the applications are. And then they have different network traffic for different source destination pairs or whatever. And then each day, the value is different for each key. And if we use the sticky randomness to sample each instance, we can do useful things with it, like compute relation between different days and so on. We'll see examples. So these coordinated samples actually have many different benefits. One that is why it was invented in the first place by statisticians is the stability. So if we use this sticky randomness and weights evolve, weights change, but we always want to keep a sample with respect to the current set of weights. Then with the sticky randomness, we can do it while minimizing the changes in the sample. So often these kind of coordinated samples are used as representations of different data sets, different text documents, data from different days, and in that case, you can do queries, inter-instance queries, for example, similarity queries. And you can just work with these representations and get much more accurate results because the samples are coordinated. Sometimes coordination gives you efficiency, like we've seen in the graph sketching examples. Without coordination, we couldn't get very efficiently samples for all nodes. So this is like a recent application, which doesn't have to do with efficiency, but basically if you have multiple probability distributions and you get a sample from each one, if the samples are coordinated, you get high agreement because like the randomness is shared, it's external to all the distributions. And then each time you do it, you will get the same sample from each. And this is very, very useful for privacy. If you know sample and aggregate kind of schemes where each part of the data contributes some prediction, and then you want to aggregate the predictions, then agreement is very, very important. And sometimes, like if you think about, that's just on top of my head, LLMs, there is a very diverse set of possible answers. There are maybe like 100 possible next tokens to predict. And then you want, and you want agreement. So you need to do coordinated samples will give you this agreement. If there is time, I can show you some experiments with that. Okay. Another useful property of coordinations is what multi-objective samples. So suppose you have many instances and you have a sample for each one. So the samples overlap to the maximum degree possible, and that means you need much less storage to store samples that are good for many different instances. So it will optimize kind of the storage that you need for that set of samples. So let's talk about multi-objective samples. So basically, just think of it as you have a different set of weights instances. You take a sample of size k from each instance, and then you just take the reunion. And you can do the estimator of that type in a way that you only get better results if you had just the sample of the one probability distributions. So estimation-wise, you can just gain. And you gain storage. Okay. So, okay, so here is just like one example. You have set of keys, you have 3 different set of weights that correspond to their weight, height, and age. And maybe there are some correlations. And with a single multi-objective sample, you can store fewer keys, and you can answer linear queries accurately with respect to each one of these sets of weights. So basically, core sets can also be viewed as multi-objective samples. So here, so basically what you want here, so okay, so let's say just look at classic centrality. So you have query points in a metric space, and for each query point, you want to estimate its sum of distances or sum of distances squared to all the other points in the point set, to all points in the point set, okay? So here, the instances are basically you just take a point. Every point corresponds to an instance, and the weights are basically its distance or distance square, whatever, from all the other points. So the nice thing here is that if you take coordinated samples of the whole thing and allow for soft PPS, one small sample size will do. You can estimate for every query point the distances to all other points. And the same goes for clustering. Here, every query is a tuple, and you want to estimate the sum of distances of all other points in the cloud to the tuple. So it's many, many different set of weights. But the multi-objective sample, if you allow for soft PPS kind of little changes from the actual weights, if you allow for that, it's the total size of the sample you need is just proportional to your the k, that's in the k tuples times over epsilon square, which is the accuracy that you want.
Sorry, so I mean, like, the trivial bound would be log n over epsilon square, and you're saying that you can get rid of the log n because they're actually, like, if n was the number of points, then I could sample separately for each, or I could just sample one for each.
So you need like 1 over epsilon square for each.
Or I could just take one sample and apply union bound, but then for that, I'd need log n times, and here you're getting rid of the log n.
One sample, okay, so it's weighted sample. So suppose if you can't do it like this exactly, because then for every point, in principle, there are some points that are very far. So you want to sample proportionally to the distance, but from every different viewpoint. So this is kind of the magic of corsets. But it's just the same kind of framework of, I'm just putting it in the framework of multi-objective samples. So basically all these different instances with potentially very different sets of weights, the multi-objective sample is small, which is why corsets work. Okay, so here is another place where the multi-objective samples are small. So here you have multiple sets of weights assigned to the keys, but they are ordered in some ways. The first key always has larger weight than the second key, and so on. And then, okay, here k is the sample size k, but so basically, if you take a union of all these samples, coordinated samples of all the possible decreasing sets of weights, it will, the total size of the sample, if k is the size of each sample, the total size will only increase by log n. So this is very useful so basically it suffices to take coordinated samples of all the unweighted prefixes of this order, and it will give you everything else. It will give you a multi-objective sample that is good with any decreasing set of weights. And then you can do estimate linear queries of this form. You can take any kernel, any decaying function, and estimate that satisfies this, and you can estimate the total sum. So this is, so for example, you can do it with data streams. You look at elapsed times from the start of the stream, and you look at, you want weight that kind of decreases with the elapsed times. So the same sample is good for any window and any decaying function. So, and you only need the sample size of k log n to cover all sliding windows and all decaying functions and be able to get good estimates. Okay, so now with the graph sketches, this also comes out with a kind of a little bit more complex graph sketches called all distance sketches. So here, so before we said, oh, for every node in the graph, you want to get a sample of the nodes it can reach or its neighborhood. So now you want samples with respect to all neighborhood radiuses together. So the all distance sketches are basically it's a multi-objective sample for each node of all the possible neighborhood radiuses. So there is here a coordination across nodes and distances, and to cover all neighborhoods together, to be able to estimate all neighborhood sizes or all decaying functions of distance, you just need to store a k log n sample at every node, which is the size of the multi-objective sample with respect to all neighborhood sizes. And then, and the nice thing also that this can be computed near linearly for all nodes. Okay, so this all distance sketches have a lot of nice properties. The one thing that kind of relates to this monotone multi-objective sample is that it gives you, you can do this type of queries, estimate centrality, estimate for each node, sum, like basically a sum over all other nodes of some decaying function of the distance. That includes all neighborhood sizes, and it includes every decaying functions of the neighborhoods. It's called the centrality measures of the nodes. The coordination between nodes allows you to do actually much more, but we won't get into that. It gives you, the same data structure gives you basically optimal approximate distance oracles. Just take all distance sketches of every two nodes. You can estimate their distance for unweighted graph with optimal known bounds. Not unweighted, sorry, undirected graphs. It can be weighted. It can, you can compute similarities between neighborhoods. So these things actually had some practical impact. So it's nice that that happened. And you can also compute joint coverage of multiple nodes, find all the number of nodes that are within distance 5 from some list of nodes. You can do all this just by working with the sketches of each node, which can basically be computed by near linear time. So these are graph sketches. Okay. So now I'll talk about how to sample, how to compute such samples over data that is in its raw form. It's unaggregated. So basically, just show some techniques. So what is unaggregated raw data? So it can be like distributed or streaming. So basically it's the standard streaming model also. Every data element has a key and a value, but multiple elements can share the same key. So for example, here there are 3 elements with the seahorse key. And then we define the value as a function of that collection. So 2 natural ones are max aggregation. Okay, so if there are multiple occurrences, we just want to take the max. So for this data set, the max for the seahorse would be 8, and the max for the other creature would be 5. And or we can look at sum, which usually in streaming people look at sum or some function of the sum. which is the sum of all these weights. But the data is presented in this way. And then we want to compute the sample. So the sum would be this for this data set. So the naive way to do it is just to aggregate the pairs using some big structure of size, which is the number of distinct keys in the data set. And the goal is to work over the raw data via composable structures of size that is about the size of the end sample that we want, and be able to sample, get a PPS sample according to the max aggregate or according to the sum aggregate. So let's start with the max. It's very simple. So we use a hash-based sticky per key randomness for every key. And then we locally map each element. So we look locally at each element, which is a key and a value. And we map it to a different type of element with the same key, but with a value that is the seed of the key divided by the weight. And what we do with that is we kind of aggregate all these E star elements and we keep, during the aggregation, we can use just a composable bottom K structure to find the K unique keys with the lowest scores, okay? So if we see a key twice, we just keep the occurrence with the smallest score, and we keep track of the K unique lowest scores overall. So this is very efficient to do with the data structure of size K.
Is this because the max is like the min of the reciprocals and you're using what you did before with the min of the exponential random variables? Or?
This because the seed is fixed for everything, so the minimizer of that is just the maximum value. This is like for max aggregation. We just want, so now we want to sample with respect to the max of all the occurrences of the key. So we will soon, thanks. So basically, the one that will survive is the one where the value is the maximum. And that way we get basically a PPS sample without PPS war sample without replacement with respect to the maximum score. So this is like a generalization of distinct sampling of the cardinality sequence. Yeah.
Okay, but at this point, this doesn't use any property of the exponential distribution.
No, it doesn't. You could use any distribution. Yeah. Because, yeah.
So what happens if your final K values have the same key twice?
If the final?
Isn't it possible that the K minimum, the K minimum value at the end, you can have the same key multiple times?
Oh, you just throw it out. So when you merge, you have two size K tuples kind of, and if they share a key, you just take the one with the smallest occurrence, and you throw away the other, and you will still end up with K keys, because it's even if the two parts have exactly the same sets of K keys, you will still, when you merge, you will still have K. So yeah, that's a good point. Okay, so. And now, how do you sample this unaggregated data with respect to the sum? Okay, so here you also do this local mapping of each element to E star, and here you do something else. The new element has the same key, but the value is exponentially distributed, the random variable with parameter that is the value of that element. And then you do, again, the aggregation using a composable bottom K structure, and you keep, again, the lowest score for each key. And the only thing that was different is kind of the mapping. And this works because the minimum is an exponential random variable with distribution that is the sum of the values, which is exactly what we aggregate from. So we can just get a PPS war sample over this data very efficiently in streaming or distributed. So
something fresh randomness, but previously when you...
Oh yeah, so here actually, yes, so exactly. So here we use fresh randomness, and that's necessary. We don't use sticky randomness. The previous one actually used sticky randomness. Yeah. So it was.
If we are merging from two different...
So we can. So here we lose that property of the sticky randomness.
Yeah, but previously, how do we make sure that they get the same random file?
Oh, you can use a hash function, and just like simplify. You can use a pseudo-random hash function and assume it's, here we assume it's random or local, whatever. Okay. So what's the caveat here? When we did max aggregation, we actually could recover the weight. We got our sample included the weights. And here, our sample is a perfect sample with replacement, without replacement, but it doesn't give us the weights. We have scores, but we don't have the weights. And so we need to use kind of different estimators to work with this sample because it's missing some information. And there's also no way for us to track the weights in the streaming or in this kind of framework. So what can we do? So one easy solution is to make kind of another aggregation pass over the data, another pass over the stream, and then we know what's in our sample. So just for what made it into our sample, we count all the weights, and then we do that. A solution that works for streaming, but not for generally distributed data, is to kind of collect weights from the time the key is kind of in the sample. And this is a bit delicate because you need to adjust this weight. But the magic here, so you need a different estimator that kind of inverts. So you don't end up with the actual weight. You end up with some partial weight. But you can kind of invert it so the linear queries that you're estimating is still okay. So basically, we still can get the optimal bounds for linear queries over these weights, even though you don't have the exact weights and you cannot use inverse probability as is. You have to kind of invert it in some ways. But the nice thing is that you really don't lose. So, okay. So now, okay, so we've seen some of the weights and we've seen max. But you can, so people in the streaming literature and, okay, I wasn't giving any references, but starting with Alon Matter-Segedi, they looked at general functions of frequency. Okay, so now basically the weight that we want to sample with respect to is some function of the sum of the weights, okay? So we know that some functions are very hard. For example, we can't do anything that is a small space with when the function is super quadratic in the sum of the values. But what I'll talk about here is the two transform-based ideas. One that kind of reduces many functions of frequency that in some category that we call concave sublinear to the max distinct sampling problem. By reduce, I mean locally looking at every data element, generating one data element or maybe a small set of data elements, and then applying some basic aggregation on that. Okay, and then another one is via a heavy hitters transform, and that works for moments, only for moment functions, but moments between 0 and 2. So these are, okay, so the transform to max distinct works for any concave sublinear function of the frequencies. It's basically function of the frequency is what we call the sum of the weights, okay? So the sum of the weights of each key. So concave sublinear is something that grows linearly or less. So for example, all the low frequency moments are there. The power of p, where p is smaller than 1, less equal than 1. Capping functions, which are very useful in applications. If, for example, in advertising, they use capping functions a lot. So basically, if a value is over some t, you count it as t. You don't count, you cap it by t. Or a log function, for example. These are all concave sublinear functions, and you want a sample with respect to these weights. So I just described the high-level idea. These functions kind of are between the max and the sum. So there are sketches that do that mix these two element maps that we used for max and the sum, and somehow you can get sampling with respect to any of these functions. So this also doesn't have the sticky randomness. And also it's possible to do one multi-objective sample with another logarithmic factor on size that kind of covers all these functions. And also, if you don't want a sample with respect to these weights, you just want to compute these statistics. Like for example, distinct count statistics, sometimes you just want the distinct sample, or you just want the moment value or whatever. You don't want a sample because you don't want to ask more dedicated queries like segment queries. You just want to know the aggregate over everything. Then you can do something like hyperlog-log and do it with perfect randomness assumptions with a log-log size composable structures for all these functions. So this is via the transform to max distinct. Max distinct is a generalization of distinct count. So all these things can be done in kind of by reduction. Another method is if you want to do functions of frequency that are moments, up to 2. So here we use sticky randomness. And basically, this transform gives us what we want. If we want to sample proportionally to the piece power of the sum, we use, if you take this to the piece power, it's kind of like, it keeps the order, right? So it's like sampling, it gives us what we want. And here, the aggregate that we want over these elements is the top k, and top k sums, okay? So what we want is the sum. We still want to take sum over the values, okay? But somehow, magically, top k are hard. Here we have unaggregated data, and we basically want the top k sums, which is hard to do. Generally, we need large data structures, but in this case, when you apply this sampling transform, this order transform, the top k are always heavy hitters, meaning that the top always dominates the tail that comes after it. So basically, we just need a heavy hitter sketch. and to do this type of sampling. So, okay, now, okay, I'm done with time. Okay, so basically these are many ideas that originated in statistics and then evolved in computer science. Some were invented by computer scientists. They started with applications like survey sampling, but now they extend to large data sets. And they continue to find new applications. So I think it's a very good toolkit to kind of know. And so I hope you got something out of it. There is some write-up that I did the survey on that. So it's actually for large pods. So there are all the references and pointers there. Okay. Yeah, so I don't know, just the value of coordination, but I think I'm out of time, so I won't show you. I want to show you some plots. Okay. So this is for machine learning, private machine. Okay, machine learning. Okay, so I think I won't have time to explain it. So, okay, thank you.
Is there any questions for Edith?
Can you tell us what you would have told us if we had more time?
Well, it just, it's another application of coordinated sampling that was on top of my head for private machine learning for LLMs, and I just wanted to show. So I kind of mentioned it during the talk, how you can get agreement from different teachers, it's called teachers, parts of the data. And so I just wanted to show some experimental results on that. So it's just an application that is not efficiency and it's not queries, but it's just to get agreement. And agreement between contributions of different distributions. Okay. Thanks.
I also have a question. So a lot of that was based on the properties of the exponential distribution. What kind of other distributions that you mentioned, Poisson, that has other types of properties? What are other nice tricks that you would say just go on Wikipedia and check the properties of this or this one for aggregation, max or mean or things like that?
Yeah. So, you mean for priority sampling? You can usually get the same bounds, but sometimes exponential gives you the sum to mean property. So, but I think you can get a lot of it. Like if you do max distinct, you can use priority sampling for that. So yeah, so there are many different types of very useful distributions. Piotr knows stable distributions of that are very useful for something. Yeah.
Are there numerical issues you have to care about?
Not really, even though I kind of presented it as working with the continuous distributions. Usually you can basically truncate to the point that you get different numbers for different things in your sample, and then you can kind of extend them and apply them the same estimators. So it's not really an issue. Usually hyperlog-log, you just work with the exponent even. And but a lot of the general line of thinking and analysis is the same.
Well, I think there is a reception outside of the door, so let's thank Edith again. Actually, from the right.